Today, we're going to talk about molecular polarity. This is what we're talking about today. And I want to turn the lights on for a second. Today, we're going to talk about why this does what it does, or why it looks the way that it does. In other words, here at the bottom I have green food coloring and water, and at the top I have oil. Now, when I shake it back and forth like this, there's a reason why it's kind of slow and why they actually don't mix unless you shake it up and force it to. But then eventually, and I let this sit for a week without having somebody mess with it. I call this layer in between, where you can see it kind of move around, I call that the hate layer. Because water is a polar compound, where oil is a non-polar compound. And they don't like each other. They really don't like each other. And they don't like each other so much that if we do shake it up, that they will separate and get into their own side. But this hate layer here is actually where the polar substances meet the nonpolar substances, and it's kind of a funky layer. I mean, if you were to look at it, it looks weird. It looks nasty. Okay, so we want to know, what is the molecule? Because if I have a polar molecule, it will dissolve in water. If I have a nonpolar molecule, it will not dissolve in water, but it will dissolve in the oil. And vice versa. If I have a nonpolar molecule, it'll dissolve in the oil, but it will not dissolve in the water. It's kind of like if you ever painted before with oil paints. Say like you're working with red and you have that on your paintbrush and you want to change now to, say, a yellow color. You just take that paintbrush, go to the water faucet, turn it on, and all that paint comes right off, right? You guys don't paint with oil. You actually have to put it in like paint thinner or turpentine or gasoline. I wouldn't advise gasoline. But you need something that is nonpolar because the oil paints are also nonpolar. However, if you're working with watercolors, then yeah, you just wash it off with water. So what we're doing today is we're actually still using the models. I'm going to get the models out. And we're going to talk about how we can tell if something is polar or not. And I'm going to use a really nasty analogy. Okay? And I call it the tug-of-war analogy. And if you Google it, you're not going to find it anywhere. Nobody's going to know what you're talking about. But back in the day, they used to execute people by getting 4 ropes. And they'd tie one rope to one arm, another rope to another arm, another rope to a leg, another rope to another leg, and then attach those ropes to 4 horses, facing 4 different directions. Okay? There you go. Okay? So, quartering somebody. Hopefully you get nice 4 even sections as a result. Well, here's that analogy. And again, sometimes it's the gross analogies that you need to remember things. So here are my 4 horses around the central atom. Okay? Whoop. And this is me. I'm super strong here. You know that. And if I have these 4 horses move in 4 different directions, and if all these horses pull with the same amount of force, will that central atom or me move as a result of that? No. And some of you have some of you had vectors before? Know what vectors are? Okay, so like if I add up the sum of the force of this vector and this vector and this vector, these 3 vectors actually equal this vector right here, which is pointing straight up. So no matter how I turn it, those equal each other, right? So if all of these horses, or the tug-of-war analogy, everybody's pulling with the same amount of force, and the central atom does not move, it's nonpolar. Okay? And I'm going to use some great English here. No move, nonpolar. Okay? No move, nonpolar. So nonpolar means that it would dissolve in oil. Now, take an atom away. If I take an atom away, it's kind of like I'm taking a horse away, or I'm taking somebody away. I just have the rope there, but nobody's pushing or pulling. So if I have these 3 horses pulling or pushing, will the central atom now move? Yeah, as a result of all those vectors, it'll actually move downward. That, all it takes is to take one atom away, and now it's a polar substance. So now it will dissolve in water. Okay? So if you use that tug-of-war analogy and you're saying to yourself, hey, if I add up the sum of those vectors, or the tug-of-war, and the central atom moves, Okay, now all the atoms are moving unless it's at absolute zero, but this analogy works great. And say if I have these two pulling, will this central atom move? Yeah, because again, the lone pairs don't push or pull, so it does move. And we could say that that's actually a water molecule, so it is polar. All right, now there are two exceptions to the rule. If you have lone pairs of electrons, most of the time you're looking at a polar substance. However, there's always an exception to the rule. If you look at, say, the table, if you're looking at the table and you say, okay, I'm looking at square planar and linear, okay? Here's octahedral. I'm going to start with the square planar. If I take two atoms away, okay, notice now how that arrangement looks in that those four are on the same plane. They're all 90 degrees away from each other. And if I were to pull with the same amount of force, because again, lone pairs don't push or pull, would that central atom move? No. So that's not polar. Okay. All right, so now the other situation is if I look at the trigonal bipyramidal, which is down here, trigonal bipyramidal, and then we have a linear shape. Here I have three lone pairs, but my two remaining atoms are 180 degrees away from each other. If they push or pull with the same amount of force, the central atom will not move. So this one and this one are my two exceptions to if you have lone pairs of electrons. So this is nonpolar. Any other time that you have lone pairs of electrons, it is polar. Yeah, go ahead. This one? Okay. What's your concern? Okay, so since they're all on the same plane, and they're all 90 degrees away from each other, so these two cancel each other out. These two cancel each other out. So the whole thing's canceled, since they're all on the same plane. And then hopefully this one's a little easier. They're just two opposite of each other. All right, let's say that I've got, say, this scenario, okay, where these three atoms are the same, but this one's different. Do you think they're all going to, again, they're different because they have different forces as well. Will the central atom move? Okay, these three have the same amount of force. This is different than these other three. Yeah. So anytime you have different external atoms, no ifs, ands, or buts, it will be polar. Again, different external atoms, whether it's one, two, as long as there's somebody different, it's going to be polar. Okay. So here's the criteria again. If all the external atoms are the same and there's no lone pairs, this is what? Nonpolar. Good. So again, all the external atoms are the same, no lone pairs, nonpolar. Always. No ifs, ands, or buts. If you have at least one different atom, whether you have lone pairs or no lone pairs, it's going to be polar. And that's kind of nice because even if I have, say, and some of you might say to yourself, oh, I have this scenario where I'm going to have, grab the ball here. Okay, here's the red one. Okay, so say you have, I'll edit that up. Say this scenario here, okay? What do you like about that? I wouldn't do that to you because somebody might build it and say, well, it could be this way. Wah, wah. So anytime you have different external atoms, we're going to say that it's going to be polar. Yeah, Kate. Right, as long as it's not one of these two here. Yes. Okay. Sound good? Ready for some examples? Sounds like fun. Let's take a look at the homework for tonight. So the Vesper worksheet, I think it is. Nope, not that one. Where are you? Oh, I just missed it. Okay. All right, so let's take a look at ICL 3. Okay. So your homework is, I think it's 2 pages. Don't run away. All right. So ICL3 in this first category, actually let me scroll to show you. First category or first column, okay, excuse me, the total number of valence electrons, the Lewis structure in the second column, third column is the first name, second column is the second name, and then here's what we did today. So, scroll. All right, so ICL3. So let's get our total number of electrons. So iodine has 7 electrons. Each chlorine has 7, but there are 3 of those. 28. Good. Okay. And who's going to be my central atom here? Iodine, since it's our one and only. And then I'll put the chlorines around it. Okay. And let's change colors here just to be cute. Okay, so I'm going to put my electrons. So I'll give my chlorines their 8. Okay. How many electrons do I have represented right now? How many? 24. Okay. So that means I need 4 more. So I'm going to give it legs in this case, because I'm never going to put more than 2 electrons in a single quadrant. So if I do that, then I'm going to separate it with arms, legs, antennas, whatever you want to call it. All right, so let's talk about potential. What is our potential for this molecule? Got 2 5s, 3 5s. Everybody agree? So we have 3 external atoms plus 2 lone pair. So again, whoop, go back to the table there. So that means I'm working out of this column. So the first name will be what? Trigonal bipyramidal. And there were how many lone pairs in that? 2. So I'm going to come across, and it should form a T-shaped planar. Good. Oop, same one. And okay, so it'll be trigonal pyramidal, and what was it? T-shaped planar. All right, so let me build this. Okay, so it has 2 lone pairs of electrons, and it forms a T. So is this polar or nonpolar? Celeste, what do you think? Polar or nonpolar? Why? It's missing 2. So these 2, they're opposite each other. So these 2 do what to each other? Cancel each other out. And then this one would cause it to move. Yeah, Kate. It's polar. So when looking at it, think about it like this. So these 2 cancel each other out because they're directly opposite each other. But this one is not. It's actually perpendicular, and so it push up. And keep in mind, the lone pairs don't push or pull with this analogy, and it's a good one. So this would be polar. Okay. Make sense? Yeah.
Okay, I understand that, like, if you model it out, but how are you supposed to do it without?
Good. So what we're doing is we're kind of theorizing at the moment, and then tomorrow and Thursday we're going to build them and solidify it. So remember the rules that if you look at it, let's stay there. So again, somebody was saying, if I looked at, say, these 4 across, and then these 2 here, other than these 2, if I have the same external atoms, everybody will be polar in the white, except these 2 if they're the same atoms. The second name. So what it actually forms. So let me ask you this. Any of these 5, if all the external atoms are the same, will be polar or non-polar? If all the external atoms are the same, they have no lone pairs. So all 5 of these up front have no lone pairs, So if all the external atoms are the same, then it's always going to be nonpolar. Once we start losing atoms and have lone pairs, then it starts to get polar. Now, if you have different external atoms for any of these, this is what. If the external atoms are different, then it's automatically polar. So these are the only two that are special in that if you have the same external atoms, but you have this shape, it's going to be nonpolar. And again, that'll be solidified with you building it tomorrow. So today it's okay to make mistakes on the homework for your polar and non-polar. But everything else, all the other things should be, hopefully, pretty straightforward. And I did put on there that one. Okay? And tomorrow you'll be building these and talking about these and having so much fun. All right, to give a few more examples about polar and nonpolar molecules, I've got a few models here. And so looking at, say, this first one, again, when all the external atoms are the same and there's no lone pairs, we're going to say that that is a nonpolar compound. So regardless of the shape, whether all the external atoms are the same, okay, these are all going to be nonpolar compounds. Because again, using the tug-of-war analogy, or the analogy that I've shown you guys in class, is that all of these are pulling or pushing with the same amount of force, and if the central atom doesn't move, no move, nonpolar. Same thing here. All those are pushing or pulling with the same amount of force, no move, nonpolar. And again, no matter how simple, and I don't want you to worry about double bonds or single bonds or even triple bonds. And if you're concerned about, say, that and say, well, that double bond's stronger than the single bond, that is a true statement. However, think about this. If you're pulling with, say, a single rope versus two ropes, does that make your force of pulling or pushing stronger? No, it just makes the bond or the connection stronger, but it doesn't do anything in terms of the force itself. All right, so when we remove an atom, so now we have this, it's a still, if I'm looking at this original shape as being a trigonal planar shape, okay, with the atom connected there, that's trigonal planar. And if they all have 120-degree angles for this atom, if I remove an atom, say now I was originally looking at SO3, now I have SO2, this is a polar compound because these two atoms are not directly opposite of each other. So the vectors, if we were to use that terminology, would cause the central atom to move. And if the central atom moves with this analogy, then we're going to say that that's a polar compound. Okay? Same thing with, unfortunately, the linear will always be nonpolar unless we have different external atoms, which that would be the only time or situation that we could ever have where linear would be polar, is if the external atoms were different. Looking at the tetrahedral shape, again, if we say that this is like carbon tetrachloride or methane, those compounds are nonpolar molecules because, again, all the external atoms are the same. There are no lone pairs on the central atom, so they all push or pull with the same amount of force. Central atom doesn't move, so we say that's nonpolar. However, if we look at, say, something like ammonia, NH3, we do have that lone pair of electrons. These three atoms on the bottom do exert a force or a vector. So if we were to add up the vectors there, they would equal that force there. So if they were all pushing with that same amount of force, the molecule would move in the analogy up. So it is moving, which means it's polar. Take off another atom. Say now I could possibly be looking at water, two lone pairs of electrons. We have two atoms. Obviously, we have a bent shape here, so that is not linear, so that central atom will move, which makes that polar. Looking at the next one, the trigonal bipyramidal shape. So again, all the external atoms are the same, no lone pairs on the central atom, so that's a nonpolar compound. Again, if you have different external atoms, it will cause it to be polar. Take one atom away, we now have the seesaw shape, okay, so the seesaw. And this does cause us to have a polar compound because the two on the opposite ends cancel each other. However, the two in the middle are at 120 degrees away, so that will offset and cause the central atom to move. Polar. If I look at a T-shaped planar situation here, so what that's doing is these two cancel each other out. However, that one causes it to push, which makes it a polar compound. Looking at, say, the last scenario for the trigonal bipyramidal shape is that these two atoms cancel each other out. Lone pairs don't push or pull. Therefore, this is a non-polar compound as long as the external atoms are the same. So that's trigonal bipyramidal. Last shape, octahedral. All the external atoms are the same. No lone pairs on the central atom. That causes that to be a non-polar compound. If we look at the square pyramidal shape, again, these four cancel each other out. However, this one lone is perpendicular to all four of those, which causes, if we were doing vectors, for it to move down or move up, depending on if you're pushing or pulling. This is a polar compound. Take away the second one. Okay, now we have our square planar shape. All four of those are on the same plane, so they all cancel each other out. This is our second exception to our trigonal bipyramidal. These are our two exceptions to the rule where you have lone pairs of electrons and it makes a non-polar compound.